All right, so I'll start. Hello, everyone. Good evening or good noon, depending on where you are. And I'm Yash. I'm Yash Gurbani from National Committee India of IAPS. And today we have Dr. Christian Beck with us for a session on statistical and nonlinear physics. Now, as you all know, that IAPS has been working to promote peaceful collaboration between students. But this year, none of our in-person events happened because of the global situation we find ourselves in. But to keep the spirit of inquiry and collaboration alive, the IAPS Events and Advocacy Group has put together this IAPS at a distance online sessions. And right now we are in week 4, and we have Dr. Christian Beck with us, who is the chair of Statistical and Nonlinear Physics Division at European Physical Society. So I'll take a minute to introduce him further. So yeah, Dr. Christian Beck is a professor of applied mathematics at Queen Mary University of London. And he studied physics at Technical University of Aachen in Germany. And then he obtained his PhD in theoretical physics there in 1988. After spending some time as a postdoc at Warwick University, University of Maryland, Copenhagen, Aachen, and Budapest, he was appointed at Queen Mary University of London in 1994, first as a lecturer, then as a reader, and finally as a professor from 2002. Since 2014, he is the head of Dynamical Systems and Statistical Physics Group with the School of Mathematical Sciences at Queen Mary University of London. And currently he's also the chairman of IAPS Statistical and Nonlinear Physics Division. A bit more about his research interests. Some of his research interests are stochastic modeling, statistical physics of complex systems, chaotic dynamics, nonlinear dynamics, and other interdisciplinary applications. So without further ado, I'll ask Dr. Christian Beck to start with the presentation. Yeah. I think.
Yeah, thank you very much for this kind introduction. It's a great pleasure for me to talk here in this event organized by the International Association of Physics Students. And I want to talk a little bit about the general field of statistical physics, nonlinear physics, complex systems. And that is, in fact, quite well represented by this IAPS division, of which I'm the chairman. So I will divide my talk into parts. In the first part, I will just talk a little bit about this division, the topics, the activities we do there, and what type of research one is typically engaged with in statistical physics these days. And in the second part, I will then come to a concrete example of a research where I'm involved. And for this example, you see that the methods of statistical physics are these days really quite very generally and in a much broader context than in the early days of statistical physics. Okay, I will share my screen now that you see what I'm going to talk about. Yeah. Can you see my screen?
Yes. Yeah.
Okay. Yes. So when we talk about statistical physics, I hope you can see these nice pictures here on the left and on the right. In fact, the areas of research that are represented by our IAPS, European Physical Society division, they are very broad, and it's including people who deal with turbulence, for example. You see here a picture of trajectories of particles in a turbulent flow on the left. And here in the middle, you see a network that is also a very active area of research in this area right now. And what you see here is a network of proteins. So we have a lot of people who are interested in biology as well. And but these are not the only topics. It's really many different things. And so if you want to know a little bit about that, here's what we have written for the aims of our division. I hope you can read it. One of the aims is indeed to, you can read it here, to stimulate the interest of young scientists in the field of statistical physics, nonlinear physics, systems. And that is just also what this talk is about. I want to show you, if you're a student either undergraduate level or perhaps even PhD level, that we do quite a lot of interesting things right now in statistical physics. In fact, if you work, let's say, in dark matter physics, then you have only one topic, basically understand what is dark matter. But in statistical physics, it's much broader, right? People have different subtopics, they have different interests, and still we use a common language, which is that of statistical mechanics and stochastic processes and network theory. What is done these days is very much non-equilibrium statistical physics. So we are not so much anymore looking at systems in equilibrium, but it is really systems that are driven by some force that are in a non-equilibrium state. A lot of people look at complex networks. A lot of people still work on nonlinear dynamic systems where the equations are nonlinear and allow, for example, for chaos and turbulence. Then another big branch of research is on stochastic modeling, on all kinds of dynamics where you add some noise and look at the stochastic properties. And in the research that I'm going to describe in the second part of my talk, I will talk about such a stochastic modeling approach. But then there are also fields like spin glasses, disordered quantum systems, pattern formation, long-range interacting systems. Just this last point is quite interesting. Everything what you learn as an undergraduate student in statistical physics or statistical mechanics at your course is basically for systems with short-range interactions. As long as that is the case, the ordinary formalism of statistical mechanics works well. But if you have long-range interacting systems, then things become much more complicated. And that is also part of research of many colleagues in this field. Maybe the most important point here in this list is the last one here: interdisciplinary applications in physics, biology, economics, and social sciences. It is not anymore that in statistical physics we just look at particles in a gas, but we look at agent-based modeling, we look at living beings that diffuse, we look at economic models, we make models for in the social sciences. So for example, people even make models how fake news diffuse and things like that, right? So it's much more general these days than in the early days of Boltzmann, where you were just interested in the dynamics of the gas of particles. Well, in our EPS, the European Physical Society division, you may know the European Physical Society has about 10 big divisions, and ours is one of those dealing with these topics that I've just mentioned. And one of the way to communicate with colleagues and with students and with PhD researchers is at conferences. So we had a couple of nice conferences in the past where we were involved. The last one that was organized by our division solely was this one here: Statistical Physics of Complex Systems, that took place in Stockholm, a very nice city, in May 2019. So maybe I show you a few pictures of that. if we go onto that website, you see here, this is the Auditor building in Stockholm, and here you see a crowd of people discussing in front of the lecture room. And that was really quite a nice conference with lots of young people, lots of PhD students participating. I perhaps show you, I've talked quite generally about the topics that we have. If you now want to go into more detail of what is being done concretely, what is, so to speak, the forefront of research, then I would recommend here to look at this second paragraph. What this conference did, it was very recent developments in stochastic thermodynamics. That is the theory of small thermodynamic systems where you have fluctuations and where things become non-trivial. So small complex systems are a big topic. So-called fluctuation theorems are also a very interesting topic presently, where you look at the general properties of systems away from equilibrium. And then still people look at billiards, that is deterministic dynamical systems that behave chaotically under certain circumstances. They look at extreme events, they look at multiplex and multi-layer complex networks, time evolving complex networks, and so on. Another interesting topic are anomalous diffusion process. You know, if you have a normal type of diffusion, then the mean square displacement of a particle grows linear in time. So the quadratic mean square displacement is just a linear function of time, but there are a lot of systems, in particular in biological context and other contexts, where you have so-called anomalous diffusion processes where the time dependence is not anymore linear, but it goes with the power of time. So all these different topics have applications in many different interdisciplinary applications. And at that conference, we met and talked about the most recent developments. So just to give you a flavor how such a conference looks like, I think I show you some nice photos of what we did. And that should encourage you, perhaps, if you're interested in this topic, to take part in our next conference, which will take place in Trieste, probably in autumn 2021. We don't know the date yet precisely, but there it will be in a similar spirit that we look at all kinds of applications of statistical physics in modern systems and complex systems. Here, just some photos to give you a flavor. This is a very famous person, Laszlo Barabasi, who's an extremely famous person in networks. And to his left, you see there in the harbor of Stockholm, Ginestra Bianconi. She is a professor at my home institute here and working on complex networks, also very well known. So very famous people giving talks there in Stockholm. But of course, most importantly, lots of young people as well. That is this second photo that you see here in the middle. A lot of PhD students, a lot of young people coming and presenting posters and giving short talks as well. And here you see on the right-hand side, you see Benjamin Schäfer, which is my postdoc, who was also there, and he did a lot of the work that I will present you as an example work in the second part of this talk. Here's Raul Toral, another member of the board of the Statistical Physics division. Well, I think you get the flavor. It's a very friendly community, and we discuss a lot and have lots of ideas and fun at these meetings. So if you want to learn more about complex systems, statistical physics, I recommend you participate in our next conference in Trieste. Well, here in Stockholm, I show you just many of the pictures where people discussed. Maybe a highlight was that we put the entire conference onto a boat, right? And we made a boat trip with about 200 people on a boat. And if you have ever been to the Nordic countries, it's really beautiful to sail there. And so this conference dinner was on a boat, and it was a particular highlight of the conference. Okay, so far so good. This is more on the fun side that you see all these nice photos. But I now want to show you an example type of research that is currently being done. And for that, I start a new presentation. Just give me a second. Can you see this slide? Is it all right? I hope so.
Not yet.
Can you see it?
Yes.
Okay.
Yes.
Okay.
Yeah. Now
try to get rid of this black thing here. Yeah. Okay. Yeah. So this is now about 15 minutes on research, and this is just to give you a flavor where we are in statistical physics. There are many directions of research, but this one is something that I have been personally involved in, and it is a so-called super statistical methods for complex systems. So what is that? Well, if you learn statistical mechanics at undergraduate level, then the professor tells you, oh yeah, we have many particles there, and the system in the canonical ensemble has a particular temperature, and then we derive this and that given this bath of a given temperature. The temperature in statistical physics is usually described by beta to the -1, so beta is the inverse temperature. But if you have a non-equilibrium situation, like this one sketched here, then you see you may have different temperature slices, different regions with different temperatures. So a particle may first be here in this area with inverse temperature beta1, and then proceed to another area with temperature beta2, and then proceed further. And in this way, you have a mixture of different temperatures in non-equilibrium situations. And there has been a lot of progress for these types of non-equilibrium systems under certain assumptions. And so what I'm going to talk about is about the super statistics approach. It is kind of an approach where you integrate over many intensive parameters. So that means you look at an ensemble of thermodynamic systems, each with a given inverse temperature, and then you mix all those together and come to a description that is much more complex than an ordinary equilibrium system. And rather than boring you with all the details of this theory, how that works, I show you some nice examples where I think these super statistical methods are particularly useful. One example is acceleration statistics in turbulent flows. Another example is the momentum statistics of measured cosmic rays. There are very new data from the alpha spectrometer on the space station. And finally, I come to something that is much more real life, namely power grid dynamics. Sustainable energy systems are also described by such a type of heterogeneous statistical mechanics. So I give you a little bit of a flavor. We saw this picture already. If you have ordinary statistical mechanics, you usually have a Gaussian stochastic process. Think of the diffusion process of a particle, the probability density to find the particle somewhere, or the probability density that this Brownian particle has a particular velocity. That is a Gaussian distribution, a normal distribution, right? But if you have this situation that I just mentioned, if the Brownian particle moves from one patch with a given temperature to the next patch with another temperature, and then, so to speak, two different Gaussians mix together with a different variance, right? With a different width, because this the temperature is higher, then the Gaussian distribution will be broader. The interesting thing is, if you integrate that, and if you look at the long-term behavior of such a particle that is locally described by something Gaussian, then you get very interesting dynamics. And overall, by this integration, you get distributions that are very different from Gaussian distributions. So this is the main idea of those people who currently deal with these types of inhomogeneous systems. You have locally, let's say, a very simple dynamics in ordinary Brownian particle at a given inverse temperature. And then superimposed to this is a stochastic process of these inverse temperatures, which describe the varying environment of the Brownian particle. So since it's a superposition of two processes, a simple local dynamics and the varying environment, that is these days often called the superstatistics. The super comes from superposition, right? It's not superior to something, but it's a superposition of a kind of many statistical physics descriptions in one go. And if you do this description, then believe me, you get very strong tails often in the probability distributions that are not at all Gaussians anymore, but that decay with power laws or with stretched exponentials. So it's interesting mathematics and interesting applications as well. In fact, what I've shown you was just one example of thinking of a Brownian diffusing particle, but you can basically take your favorite system in which you're interested in, that may be in biology or in finance, and then make that system super statistical by regarding the parameters of your system as being inhomogeneous, being random variables as well. So rather than looking at your favorite system with fixed parameters, you make the parameters of your system evolve in time or in space as well. And that very often leads to very realistic descriptions of what is going on in real systems consisting of a non-trivial environment. So we are going far away from this Brownian particle, much more general applications in biology, in finance, in scattering processes, in high energy physics, and so on. In a nutshell, if you learn statistical mechanics in an undergraduate course, then you have heard of the Boltzmann factor, right? That is this exponentially e to the minus beta e. That describes you the probability to find a system in the energy state E, right? That probability is proportional to the Boltzmann factor e to the minus beta e, where beta is the inverse temperature. But as we are now doing super statistics, we have to kind of mix together all these different betas that we have in the system and weight each beta with the probability density f of beta, which is probability distribution of the beta in your complex non-equilibrium system. And of course, f of beta can be anything, but one actually finds in real systems particular distributions very often, like the chi-square distribution or the log normal distributions. The interesting thing is that many results in this generalized statistical mechanics can be proved for general f of beta, so we don't have to assume very much what the properties of f of beta are. A lot of results, at least in the statistical physics context, can be proved for general beta and general f of beta, general distributions. I show you a few examples where these types of super statistical methods have led to success. Here you see an interesting picture that is a trajectory of a single test particle in a turbulent flow, right? A small test particle that is embedded in a strongly turbulent liquid. And you see this particle behaves erratically there, circulates around, and the color that you see there in this plot indicates the acceleration state of that particle. These are true measurements which have been done some 19 years ago by Bodenschatz and others. And what is quite amazing, if you translate this color code of the acceleration into real data, then these tiny particles in a turbulent flow are incredibly strongly accelerated. So one measures their accelerations of 16,000 meters per second squared. They're immense accelerations, which are possible because it's just a tiny little particle that is embedded in this turbulent flow. But that is the reason why, well, if you want to learn something about biology, think of that as a mosquito, right? This tiny little particle. And if you want to avoid mosquitoes in your room, what do? You put on a ventilator that makes the air in your room turbulent. And then the mosquitoes disappear because they don't like to be accelerated to 16,000 meters per second squared. So that is a trick how you can avoid mosquitoes in your room. Just make the air a little bit turbulent and they will disappear, right? But here you have concrete measurements of tiny test particles in turbulent flows. And what one sees is that the probability distribution to see a particular acceleration is strongly non-Gaussian. It's not at all a normal distribution, but it has for large accelerations, it has heavy tails, this probability density. So here's the probability P of A to observe an acceleration of a particular strength, and here's how often that acceleration occurs in the measurements. And what one sees, it's strongly non-Gaussian, so we cannot use Gaussian stochastic processes for that. But if you do a kind of super statistical model, which is this equation 1, you see here's just an ordinary Boltzmann factor, if you like, and here's then a probability distribution of beta of this variance parameter, which in this case is chosen to be a log normal distribution. Then you get this solid line here that fits the data very well. And in this way, people in recent years have more and more understood non-Gaussian probability densities, not only in turbulent flows, but also in other systems. So this is a nice application to concrete systems where you can learn from generalized methods of statistical physics something new. Let me show you another example, which I personally also find very interesting. It is a completely different system. You know that on the International Space Station, there have been recently some fundamentally new physics experiments on cosmic rays. So on the space station, there's the alpha spectrometer, which measures different particle species in the cosmic rays, right? Our Earth is all the time bombarded by particles, most of them being protons, but there's also electrons and positrons and heavier nuclei. They bombard the Earth all the time, and they come with a certain momentum spectrum, right? So you have, if you like, a probability density to find a cosmic ray particle with a given energy. And that has now, in recent 2-3 years, been measured very precisely on the space station by this alpha spectrometer, a huge collaboration. And what one finds there is, again, there's not at all a Gaussian momentum statistics or exponential one. Rather, you find power laws, heavy-tailed distributions, right? So the probability to find a cosmic ray particle with high energy is pretty high, much higher than we would expect for a Gaussian distribution. And these are typical data here. Here you see the flux of cosmic ray particles, that is to say, the probability density to find the cosmic ray particle with a given energy. And here is the energy from 1 GeV to 10 GeV to 10 to the 3 and so on. And notice this is a log-log plot. And what you see in the log-log plot is more or less a straight line here. These are the data for electron and positron cosmic rays. So how often an electron with a particular energy arrives in this spectrometer from outer space. And it is a log-log plot. And as you know, if you have a log-log plot and a straight line there, that means you see a power law. So this is very different from Maxwell-Boltzmann statistics in classical statistical mechanics, where you would expect to see an exponential decay of the probability with the energy. But here you see power laws. And again, these power laws can be very well understood by doing superstatistics. The idea is that you see here in the spectrometer a mixture of many, many, many different scattering events that produce these cosmic ray particles. And each scattering event takes place at a different local temperature. In fact, one can also relate it to QCD processes which take place at very high thermal temperatures. Maybe some of you have heard of the Hagedorn temperature. It's sort of a boiling temperature of nuclear matter. And if you then assume that this boiling temperature has a lot of fluctuations, that is to say, there's a function f of beta that describes the distribution of this temperature, then you can explain these data quite well. And this is an example of theoretical prediction. And these are the straight lines that basically correspond to power laws that fit the data quite well. Well, for some of you, all this may be a little bit theoretical. After all, we are here on the Earth and we want perhaps to understand more our daily life rather than cosmic rays. So for those of you who are more interested in concrete applications here on Earth to pressing problems like sustainability and environmental physics, here's my last example where super statistical methods borrowed from statistical mechanics can be useful. So that is perhaps the last 5 or 10 minutes I want to talk, and then I'm happy to answer your questions. So you all know we want to reduce CO2 emission, right? Every decent country wants to do that. We want to avoid global warming. And how can we do that? Well, one thing is to have less transport, but if you look here at this diagram, the main part is this blue part. That is the CO2 emission by the sector of electricity and heat. Now, you may say, oh, electricity is very clean, it doesn't emit any CO2. But what is meant here is the dirty power plants that you still need to produce electricity. And that electricity is then, a lot of it is used for heating purposes or for air conditioning purposes. So in London, for example, where I'm based, a huge amount of electricity is used for the air conditioning of all the commercial buildings in the city. Now, if we could somewhat produce the electricity that we need for that in a cleaner way, then that would certainly help us to reduce CO2 emission considerably. And that is what is going on presently. You may know some 20 years ago, the power grid had the following structure. There was one dirty power plant here in the center, a big power plant, and that then the power was distributed in a network. But what we are currently doing is we proceed to distributed energy systems. So you have wind farms here and solar panels there and very small power plants and local electricity production on the roof of your house and so on. So this transition is going on at the moment. And of course, one then wants to understand this more complex system where you have local production of electricity and local fluctuations in consumer demand and things like that. So that is, you may be surprised, another interesting area where statistical mechanics methods are currently being applied. We have a very interesting observable. You know, as a physicist, you always need something that you measure and then you make your model for the measured quantity. For the power grid or for the electricity consumption, it is actually an interesting variable that many of you know, but probably have never thought about it, containing that information. In the power plug, right, the electricity comes with 50 hertz frequency, or in the US or some other states with 60 hertz, but usually it's 50 hertz. And now if you do a precise measurement, then you see there are tiny fluctuations of the frequency around this 50 hertz. So it's again stochastic behavior, right? So sometimes the frequency is a tiny little bit smaller than 50 hertz, and that you can translate into the fact that then you have a lot of demand by consumers. The turbines work hard to produce electricity, and more power production is needed. And sometimes the frequency is a little bit above 50 hertz, and that you can translate into the information that if that is the case, then there's currently less demand by consumers, there's a surplus of power, you need to get rid of power. So there's a stochastic process around these 50 hertz, which contains a lot of information about the complex system that underlies the power grid. Now, here are concrete measurements that we did with some colleagues, and that has been published some two years ago in this journal. Here you see, here's the time, right, over one day from 0 o'clock in the morning until the evening. And here's this frequency as a function of time. Here you see the 50 hertz, that is sort of the average value. And you see all these fluctuations here, right? And in the evening in particular, you see quite rapid fluctuations. And these are actual measurements, right? You can do these measurements very easily at your home, where we can send you a measuring device if you're interested. You can take these data yourself. And what you will then also see is every 15 minutes or so, there are sudden jumps here in the frequency. It goes a bit down here as well. These are man-made jumps because in the electricity system, people trade the electricity. And at these intervals, a new batch of energy is being traded, and depending on whether it's needed very much or not, it will lead to a tiny jump here in the frequency. But as you can see, or as you may guess, these fluctuations around the 50 hertz are not at all a Gaussian stochastic process. The power grid and all the consumers and the demand fluctuations are very complex, and they yield non-Gaussian distributions. So here the gray shaded area is a measured histogram of frequency fluctuations around the 50 hertz. And the orange line is a Gaussian distribution. It would be a parabola in this logarithmic plot. But what fits the data well is this dotted blue line, which we call a Q-Gaussian. It is a particular form of a power law distribution for which we have developed models that is describing the distribution of power grid frequency fluctuations. And if you're a mathematician, you can understand how this Q Gaussian, which is this power law, arises out of the superstatistics with this formula and a particular distribution, which is called the chi-square distribution. But I don't think I want to go into these details here. Just it shows you as an example that systems, complex systems like the power grid, are now analyzed with modern methods of statistical mechanics, and the distributions that we have there are not at all the ordinary Boltzmann factors, which would be just an e to the minus b to e, but they are integrated Boltzmann factors with a distribution f of beta, where beta in addition fluctuates. It's kind of a relaxation variable in the power. If you're interested in more of these details, one can also look at correlation functions of these power grid fluctuations, and they are then very different for the different grids. Here's a grid in Mallorca, here's another grid in the UK, here's the Nordic grid, and you can see then from the differences in the correlation function that is measured in the various grids that there are different policies and different control mechanisms in these various grids. And you can also then try to improve the performance of the grid based on such measurements. Good. Another final thing I want to briefly show you. After all, we need to understand the statistics of sustainable energy generation by wind power, by solar power. And here you see some plots of the probability density of solar energy production and wind power energy production. And again, this is a logarithmic plot. And you see it is not at all a Gaussian distribution, which would be this parabola in the logarithmic plot. Has heavy tails. So in order to understand sustainable energy production, there's no way around it. We need to understand the dynamics of non-Gaussian stochastic processes. We need to go to more general versions of statistical mechanics than those that Boltzmann in the early days was accustomed to. Good. Many other systems are being described by similar techniques of superstatistics. What I've shown you was one example. I think this is a good way to stop here. And as a summary, I would say maybe this one here is interesting. For the power grid, really many different things influence the fluctuations that you see there. It is the trading, so it's a man-made trading process taking place every 15 or 30 minutes. It is demand fluctuations of people. So people, of course, demand more energy in the morning than at night. And then you have fluctuations from renewables. The wind power fluctuates the input, because if there's a strong wind, you have a lot of wind power. But if there's no wind at all, then you don't get anything from your wind power, right? Then there's storage batteries. People have electric cars. Sometimes they charge them, sometimes not. They can be used as kind of storage. So you see that that is what we really call in statistical physics a complex systems. It's many different components which are interacting in a very complex way, and in a way that is not fully understood so far, but where a lot of people in statistical physics are now starting to work and starting to make suitable models. So if you're interested, that is a topic which you can learn at our EPS conferences, or I can also, if you're interested in particular topics, I could also point you to groups who work on that moment. So maybe yes, I think that is the end of my talk, and I'm happy to answer questions now. Let me just stop the screen sharing. Okay.
Okay, so I'll be waiting for questions at all our platforms, at YouTube Live, Discord, and other platforms. And yeah, I mean, until then, I'll ask some questions that I had during your presentation. So should I go ahead?
Yeah, please. Yes, yes.
All right. So I mean, one of the more interesting things that have happened recently, is we have seen the pandemic and how it has been like a complex phenomenon in action. Like there's been a lot of talks about disease spread on transmission networks, and
Yes.
you mentioned network sciences in your presentation. So I wanted to ask, how can people working on complex systems, how can they model this and be contribute to modeling the pandemic and more such socioeconomic systems in general?
Yes, so COVID-19 modeling is also a very topic. A lot of papers have been written in the past, and many, many different approaches. And I'm also aware that people model this transmission of the disease in various ways. So what I've shown you in the previous talk, I do know of people who try to predict, for example, the infection curve, how many people are infected at which time, given the actions of the government or the non-actions. And there, for these prediction methods, I do know of people who applied similar methods based on so-called Q exponential functions. That is one topic, but others, as you say correctly, look at network dynamics and concrete infection models. And this is a very hot topic of research, has always been infection of and transmission of diseases, but it has become extremely important in recent months due to COVID. And, as you know, the dynamics how diseases are transmitted has completely changed from 200 years ago, simply by the fact that people travel by aeroplanes and the disease is transmitted extremely quickly. So there are, I'm sure, hundreds and thousands of papers to deal with disease processes and networks, and it's a very important topic of research.
Okay, I'll ask one more thing. Like I saw your profile and you recently published a paper on air pollution statistics. So would you like to talk a bit more about that?
Oh yes, I mean that is a very new thing, and we have worked indeed on air pollution statistics. We had one paper early this year where we looked at pollution data in London, and as you can imagine, there are strong fluctuations. In fact, these fluctuations of the concentration of the various pollutants depends on the weather conditions, it depends on the emission rate, it depends on the time of the year, the temperature, it depends on all kinds of things. And if you then look at the probability to find a particular pollution concentration at a particular place, then that again leads to interesting distributions. And we found similar as for the power grids, although it has nothing to do with that, we found again heavy tails in these distributions. That is, say, a high pollution state is much more likely than you would expect from normal Gaussian fluctuations. So one can then again make super statistical models of that. And that is an interesting, very new area of research. So I hope that we can do even more research on that. We also have a recent paper, in fact, with collaborators from India, where we look how the pollution has changed due to the lockdown, and we compare the two megacities, Delhi and London, and you will see that due to the lockdown, air quality improves rapidly. It's of course a terrible cost. Looking at these data, we have estimated what one could possibly do under normal circumstances to still improve air quality. And then it was very interesting to compare the city, India, Delhi, with London, because the circumstances are very different. In London, you may know that already 10 years ago, people started to make very strong restrictions on diesel cars and things like that, that have led to a significant improvement of the air quality. And we could then see that, that indeed statistical mechanics can apply to these types of time series as well, and give useful predictions of concentration. But that is work in progress, very recent work, and I hope to work more on that. But as you see, quite generally, these methods of statistical physics, they are now often useful for real problems of mankind in real situations. It's not anymore that this is just academic, but we need to build the best environment and analyze these time series, and you understand why pollution is sometimes very high, and if it is high, what is the probability to find such a state.
So yeah, I mean, thank you for sharing about this recent work in progress, and that really sounds like a very interesting idea. So, I mean, there are more questions from the audience. So, one of the questions is that what are the main challenges of the modeling, and do experimental observations take long to occur? Like, how does that work out? And does this depend on the specific application within the field of specific application within the field of statistical and nonlinear physics? So these are the three questions.
Okay, so we do work with experimentalists indeed. I'm a theoretician, right? I got my PhD in theoretical physics, and now I'm a professor of applied mathematics. But as you can see, all these models are only getting flesh if you really interact with experimentalists. So in turbulence, I've worked with Harry Sweeney in Austin, Texas. He gave me fantastic data, which then inspired the theory. For the air pollution, we have data from the London Air Pollution Network, which are freely available. Everybody can look at that, and they have been taken by sensors, and we talked to the people who took the data. For the power grid, you may be surprised there are also huge amounts of data, and we're currently building up a database for these power grid fluctuations in various European networks, and hope to make them freely available. But you may be surprised, the electricity companies, some of them don't give away their data. Maybe they are nervous of what the signal looks like. So, but these data can be taken by everybody. You just plug in this measuring device in the room, and you get a fantastic set of data. So we strongly depend on data in this modeling, and it's good to talk to people who take the data. For some data, you have to wait a long time to get a significant amount of data that is well described by distributions, so that can take some time. But I think it is important to produce models that do reproduce the experimental data well. That is no difference here in statistical physics to other areas of physics. We, after all, we want to explain the data with a good theoretical model.
Yeah. Thank you for the answer. One more question is, do you consider international collaboration important for this field?
International, oh, definitely. As I said, my collaborators are from all over the world. The most recent collaboration we had was in fact with a group from India on air pollution. It was so interesting to see what is the same and what is different in Delhi and in London in terms of air pollution. And it is extremely important to have international collaboration. And that is also the spirit of the European Physical Society, for sure. You will see science proceeds in an international way. There are no borders whatsoever scientifically, and we should talk to each other and continue this international collaboration as much as possible.
Thank you. One more question is, how did you decide to study and research in this field?
Oh, that was sometimes a random trajectory. I mean, when I was studying, you will be surprised. Later in life, I wrote a book on statistical mechanics, but during my undergraduate studies, I found it the most heavy subject I had because it was not so easy to understand what you do there in physics. So it's sometimes a random effect how you evolve, but I've always been interested in statistical physics because it's a very beautiful area, and also chaotic dynamics, nonlinear dynamics, nonlinear systems in general have a rich structure which I find interesting, and the evolution to complex networks, multi-layer networks, that is a revolution in the past 10, 20 years, is also very interesting in development, which has many, many applications. So I think it's quite interesting stuff which you can test with data. Always a good physics problem if you can check in your data whether your theory is correct or not.
Okay. So one final question from my side is that how do you see the future of complexity sciences in general? And do you see new ways in which theoretical and statistical physics could be applied to complex systems and more socioeconomic systems? And perhaps after this question, a closing note or a final advice for the physics students which are with us here. So
yes.
Yeah.
Oh, I think my dream would be that one can find a little bit of universal theory, because that could generalize statistical physics in such a way that you say, oh, I'm now in this universality class, therefore I apply these types of equations and get these predictions, and then I look how it is. But it's probably only a dream, because complex systems, as the name says, they are all different. Many of them have simply different features. So what I would really like, and what is the beauty of the statistical physics formalism, is that you have a priori at least a universal formalism. Yeah, you introduce some entropy function, or you introduce some free energy, then you calculate with it, and you ultimately get some prediction. But for complex systems, this is sometimes possible, but as a whole, it's probably not possible to find a universal theory of complex systems. But if we can make progress in some small subsections there, that is a great thing. So if you have a concrete problem where a method from physics or nonlinear dynamics or complex networks really helps to make a prediction that wasn't clear before, then that is a big progress, even if it's only valid for that particular type of system. Yeah, and the general conclusion would be, if you're a physics student at undergraduate level, I can very strongly recommend you to consider doing statistical physics. It's a very interesting field at the moment. It's kind of fashionable. A lot of people start working on that. It has a lot of real world applications. And even if you're not able to stay at university, these methods are sought after in the job market. I had a couple of PhD students who got very good jobs in the banking industry. They are modeling share prices rather than turbulent velocities, and also complex network theory, sustainable energy system. That all these methods have applications in industry as well, and I think people who are experts in data analytics and in physical methods to describe complex systems, they are sought after in industry, and they do good research and interesting research.
All right. Thank you so much. And thank you for taking out the time for this session.
It was a pleasure from my side, and thank you very much for the invitation to speak here.
Thank you so much. All right. So with this, we end the session. Have a good day. Thank you.
Bye-bye.